Alrighty. Looks like I have a hard one today. Okay. Wonder if these hard ones will ever become less hard. Uh, will I ever achieve enough mastery? Probably not. Okay. There is a directed graph of n colored nodes and m edges. The nodes are numbered 0 to n-1. You're given a string colors where colors of I is a lowercase English letter representing the color of the ith node. You're also given a 2D array of edges, where edges at j is a, comma b indicates there's a directed edge. Okay, it's directed, so it's not, so AB doesn't imply BA. A valid path of the graph is a sequence of nodes such that there's a directed edge from x to x plus I for x to x sub I to x sub I plus 1 for every 1 less than or equal to I less than k. Okay, yeah, okay, that's fine. So there's a direction between every subsequent edge. The color value of the path is the number of nodes that are colored the most frequently occurring color along the path. Color value of the path, okay. So what if there's a tie? Most frequently occurring. I guess if there's a tie, there's no color value. Return the color value of any valid path in the given graph. Return the largest color value of any valid path. Any valid path. Or -1 if the graph contains a cycle. Okay. A cycle being something where it leads back to itself. So 0, 1, 0, 2, 3, 4. So obviously it should be red here. Colors are A, B, and C. Colors are... Okay, so colors are one of the 26 letters. So the largest color value being 3. The largest, it's not A. Path 0 to return the largest color value of any path. Path 0, 2, 3, 4 contains 3 nodes that are colored A. Largest color value of any path. Color value of path is the number of nodes. I see, it's not the color itself, it's the actual frequency of the most common color in that path. Okay, that's a cycle. Okay, so the longest, the most frequent, the color value of the path is the number of nodes that are colored the most frequent, the largest color value of any path. Okay, so, okay, it took me a while. So find a path that links the most of some color, any color, and return the number of times that color appeared in that path. Okay, so, okay. Objective or goal. Find path with most that connects. Find path that contains the highest possible amount of common of a color and return the frequency of that color. Okay. So what to do here? Yes, we start by making a graph of the data structure for the graph. So it's going to be default dictionary of lists, and this is going to be directed. Okay, so for every node, which is going to be A, B, in, for every pair of nodes and edges, and these are directed edges, graph of A dot append B, and can't do graph of B append A because it's directed. The whole point of this is pass, and pass need direction generally. Is that true? I don't know. And then what? And then what? So first, I guess, detect cycle. Detect if cycle exists, and then return -1 if there is. So the detection of a cycle would mean that basically if I start from any unseen node, I can, if I start from any node, if I start from if I start from any unseen node, it can't go back on itself. If I start from any unseen node, I should be better at this. Okay, so there needs to be a scene set for sure. I'm not sure if it's initialized before or after starting the nodes, but for every node in graph, if the node is seen, then continue, I want to say. So how would that work? How would that work? So you start with a node. You say you traverse everything that you see. That's connected to it. And if ever you go, if ever you arrive at a node that you've already seen, then you know that it is a cycle. Is that true? I think you need to actually start, for each node, you maybe need to start it as the first node in the scene set. Because like if you start with 0 and you say that you've seen all these, maybe there's another node 6 that goes to 0, and that's not a cycle. But if you start with 0 and you go through these scenes, and then you go back to 0, that is, okay, I need to, I'll play around with this first, or I'll make something that's maybe not optimal first. So scene starts with the node. Every node in scene. If the node is in scene, so I don't think I need this. I need to have another thing which is going to be to traverse these things. You generally want a heap. No, queue. I think you would probably want like a deck. Double-ended queue. Yeah. And we'll start it having the scene, the node here. So while the deck contains anything, let's say current is equal to deck.popleft, and then while there are neighbors, and I generally say nay is short for neighbors, for every neighbor in the graph of this current node, if the neighbor is in scene, then I know this is cycle, so I return -1. Otherwise, neighbor is added to scene. And then I append neighbors to the double-ended queue. Okay, so you start at 0, the neighbors 1 and 2, you add those to the deck, and then the next iteration you pop left, so maybe 1 gets popped, there's no neighbors, next iteration 2 gets popped, and then you add the neighbors 2, 3, 4. I think this is all fine. So can I assume that so if I have already done 2, so 0 goes to 2, can I assume that I have already tried 2? So if I had 6, and 6 is not part of this directed graph, and 6 is not in scene, so 6 goes to 0, but 0 is part of the scene set, so it's going to detect that it's going to so do I need to do two different sets, like a done set and a scene set? Scene is for the currently tried stuff, and the done is for the all things have been done for this thing. I think maybe. So I think I have a done, which is another set. For every node in graph, if the node is in done, then can skip this node. So otherwise, you're going to set scene to have it, and you're going to set done to have this node. And for every neighbor that you go over, you also say that you've done this neighbor. So I think this is no, this doesn't seem like it work. So then you go 0 to 2. If you have already seen it, then you return -1. think. Okay, so 0, these all get added to scene. And then you have another node where the node connects to something that's in scene. And then you return -1 because you think that you've actually done this, but you haven't done this. I feel like there should be a way to optimize this. but okay, for now it's going to just go as is. So right now it's just detecting cycles. And hopefully case 2 is going to be returning -1 for each neighbor in graph of the current. Oh, not while. For each node in graph. Dictionary change size during iteration. Really? Did I append to the graph somehow? Dictionary change size. Scene, tech, while, tech.left, every neighbor of the current. Huh. For every node in the graph. And then for every neighbor of that. Wait. No, that's right, I think. Okay, let's go ahead and just print out what the heck's going on here. Okay, 0 goes to 1 and 2, 2 goes to 3, 3 goes to 4. Okay, that's fine. The node and graph. Print the node. Zero, 2, and 3, that's fine. So node is 0, scene is set including 0. The deck is 0. While the deck exists, take 0 from the deck. For every neighbor in the graph is connected to 0. So 1, 2. If the neighbor is in scene, return -1. Otherwise, scene that add the neighbor. Deck that append the neighbor. So it does this a couple times. And then node becomes 2. And then node becomes 3. Dictionary change size during iteration. What changed any size? My graph is changed here. For each neighbor in the graph of the current. It's not like I'll go ahead and just print out the graph at the end of each iteration here. What is going on? Each node in the graph. So it went through 0, 2, and 3. Huh. So it went through one iteration. Huh. So I think what happened was 4. So somehow 4 got an empty list. So it was referring to the graph at 4, which made the default dictionary create a list for the entry, and then okay, so maybe what I need is a set of all nodes, and ooh, interesting. Okay, so I have a set of all nodes. Then what? Okay, I think maybe it just needs to be something like this. For every neighbor in graph of the current. So it's 0, 2, 3. So when does it index? Okay, so 4 gets put onto the deck, and then 4 gets popped, and then if for every neighbor in that graph. So if it's actually in the graph, yes. So if neighbor if current not in graph, I continue. Okay. Yeah. That was more difficult than it had to be, I think. So this is okay. Some nodes are not in graph as they are only leaves. No directed neighbor. And then skip those nodes. Okay, so I think the cycle is detected here. Let's go ahead and make another test case of a cycle. So if I had 0, 1, 0, 2, 2, 3, 3, 4, let's say goes 4 goes back to 1, this should be a cycle. Is it not a cycle? 0 goes to 1, 0 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 1. Oh no, that's not a cycle actually. 0, 4, 4 to 1. Okay, I think I need 0, 4, 0. Or maybe 4, 2. Okay, so cycle is detected. Okay, so next up is assuming that there is no cycle here, or knowing that there's no cycle here, how do I go about determining the longest path, or the path with the most common color? I could. I think it boils down to detecting which nodes have no parent. So let's determine kind of parent nodes. nodes that only have children connections, because the parent nodes would be um, where you would find the colors to start off with. But there could be a lot of parent nodes. It could be a lot of parent nodes. So, what if I made the graph bidirectional actually? So, link the children to their parents. Because if you link the children to their parents, then maybe you can come up with something regarding the frequencies. So let's say say I have a leaf here, it's red, then I look at my parents and every parent of this leaf, I say that your red color is at least 1, and then the parents would go backwards from them and combine those colors with the parents. And you know that there's no cycle, so, well, can you do that? Even if there was no cycle, say 0 went to 2 to 3 to 4, and 4 went to 1. So 1 is kind of the leaf. 1 can go to 0, and then 1 can go to 4. Then 4 can go to 3, and then 3 can go to 2, and then 2 can go to 1. Or 2 can go to 0. And that point 0 has options of going down to 1 or options of going down through this path. Okay, I don't think that feels like it's equivalent to find the parents and then iterating downwards from the parents. So if you start with any node and you have some frequency of things for that node, the issue is, I think, let's say you have like 2 paths, like 0 through 4 down to 1 and another path down to 1. They might have 2 different frequencies of colors involved, like maybe there's a lot of reds down one path and a lot of blues down to another path. And then when you reach 1, it's not like you can just pick, like, I want I want to keep the red path, because there's like, I don't know, some number of reds and there's a smaller number of blues, because maybe after 1 there's a larger number of blues, and or whatever path that you picked, there was a larger number of it, or there was less of it and there's more some other color. Alright, so return the largest color value point path. So you can okay, how many nodes are there? 10. N is the number of nodes, and there could be 10 to the 5th nodes. Yeah. Okay. And the number of colors is 26. Because each color can be a letter. I think I I think you start from the parents and you say that for any given node there's a maximum number of colors that you can reach to that node. So you keep both the red and the blue, I guess. Each node have the maximum number of colors to that node. You need to know the parents. You do need to know the parents, I think. Okay, so let's see if I can code that. So how do you detect parents? Parents would be from, so for every edge, I'll say that let's say I have a list of all nodes. All nodes, and that's going to be a set from edges. Can I actually do that? So it's going to be a set of, I wonder if I can do that. I don't think I can, but yeah. So it's a list. Each edge is a list. So all nodes, it's going to be the set from for all nodes set. There should be a better way of coding this, but for every A, B, and edges, all nodes that add A, all nodes that add B, and then when I create the graph, anytime I have a node that is the child or the destination of the edge, then it's going to be a child. So I guess parent starts with all nodes. Yeah, maybe I should just start with parents. Assume that parents is all the nodes. And remove them. Is it discard? I think it's discard. Discard or remove? Discard. The element is in set, it will be removed. However, if the element is not found, it does not raise an error. So remove is the one where it raises an error, but it could also be so because you could be discarding multiple times here, and you want to use discard rather than remove. Okay, so let's go ahead and just print out parents here, see that works. Okay, so the first test case, 0 is the only parent. Let's say that there was there was another connection between, say, 5 and 2. So 0 and 5 should be parents. Edges must consist of only values from 0 to 4. Because there's only because 5 is, yeah, because 5 doesn't have a color. Okay, so the parents were 0 and 5, that's right. There should be another way of detecting cycles using parents as maybe the starting node. So I think maybe it should be something like this. For every parent, for every node in parents. Because, yeah, because they're going to be unique, I think. Or it's going to be better than just going through all the nodes. Every node in parents. You do need to still reset the scene, I think. Okay, that made this thing not work. Interesting, because there's no nodes. Okay. So it doesn't detect that the A goes to itself. If A equals B, return -1. Okay. And just to double check, it's still detecting if this is going 4 to 2, if this is a cycle. Okay. Okay, so if I have my parents, term parent nodes that only have children connection, and I think this is kind of like, it's not quite dynamic programming, but I'm definitely envisioning like a matrix storing the frequency. So say we have color color um, uh, color frequency, color count, and this is going to be 0. For every node is going to be the outer side, and then for every color is going to be inside. So the number of colors would be what? 26? I can maybe change colors into an integer array. Okay, let's go ahead and convert colors to an integer array. Converting colors to integer array to make it easier to index. So color int is going to be the ordinal of the color letter minus ordinal of letter A for every letter in colors. I think that is probably fine. That was syntax. Okay. Okay, so 0, 1, 2 is the colors. These are the ones we're returning earlier. Okay, so I think that's fine. So determine, so I have my color ints, and then what I want is I want to start off with parents and add them onto like a stack, and then what? So if I start with a queue, double-ended queue of parent nodes, so I consider starting, let's say there was another node here that was 5, and 5 goes to 2. So 0 and 5 are the parents. I add those to the queue, and then when I pop from the queue, pop 0, and I contribute. So when you pop from the queue, I think when you pop from the queue, you're popping everything that currently has 0 in length. So the most that any color could be is 0. And you're going to say that all the neighbors of this current node, they can be reached with 1 red. So I go to node 2 and say that you can get to there with red. Going to node 1, you can say you get there with a red. And then the next pop is popping 5. Let's say 5 is blue, and 5 is only connected to 2, so you can say you can go to 2 with a blue. And then the next node that you pop might be 1. Next node that you pop is a 1. And then the next node that you pop is like a 2. That's not great. It's not great because let's say that there was a longer path to get to 2. Like, let's say there was like 5, 6, 7, 8, 9, 10, and then 2. At that point, you kind of need to restart. You need to restart how much you're getting from your 2. Like the number, the most colors that you can get. Maybe you don't always append to the start queue or the back of the queue. So, okay, so let's say you have red 0, red 2, maybe I should say 0 red, which goes to 0, which goes to 2 red, which goes to 3 blue, which goes to 4 red, and this one also goes to This one also goes to 1 purple. But let's say that there was another parent where it's like 5 blue, goes to 6 blue, goes to 7 blue, and then that connects to like the 7 connects to the 2. ASCII drawing the graph of the node. Okay, so let's say that there's something like this. So how would the queue handle this? So if 0 and 5 gets added to the queue because they're parents, and then 0 adds onto the queue 1 and 2, 5 adds onto queue 6. And then if you did that, then 1 adds onto queue nothing, 2 adds onto queue 3, 6 adds onto queue 7, and 7 adds onto queue 2. Huh. So you don't want to process 2 unless all the parents of 2 have been you don't want to process a node unless all the parents of that node have been processed. In which case, maybe you should be doing bottoms up. Maybe you should be starting with the children and then processing the parents of the children. But then you have the same issue where you don't want to process a parent unless you've done all the child of that parent to know what the best path. So I think it's maybe you have the same issue if you go from child to parent versus parent to child, because you always have this. You never know kind of what is the best parent and what's the best child to. But it is true that you don't process something unless you don't process something unless all the parents of it has been processed. If you're going through top bottom. So you go 0, you go 1, 2, add to the queue, go 5, add 6 to the queue, 5, add 6 to the queue, and then you do 0. And then when you do 0, you check to see if 0 has been have all the parents done 0. If not, then maybe add 0 back to the end of the queue. Yeah, okay. So what I need for this idea would be to keep track of which nodes you've seen and what parents So for every child node, you maybe have a set of parents connected to the child. You remove the parent from that set once it's processing. Okay. So how does this work? So I can say for every child, so for A, B, and edges, I can say, I already have a set called parents. I'll say this is the reverse graph, kind of. And for the graph, if A is connected to B, then graph of the reverse of B dot add A. Here, this is not a list, this is a set, because I mentioned I'm only going to do this once, removing stuff in the set or adding stuff to the set. Okay. So for every, so I start with the deck here, and it's going to be all my parents. My parents, and I'll say for every, so a wild deck is this. Say the node is parents dot pop left. This is a deck you need to either pop in left or pop in the right. And by default you pop in the left and you append to the right, or in general. So you have no, it's not parents, it's deck. So you take the node, technically, so the default thing that you would do is you would go through the children, if there are children. So if node is in graph, or if the node is non-graph, then just skip it, because skip it. If the node is non-graph, I think maybe, okay, I forgot to create this data structure to store stuff for the color frequency. So for each node, track max of each color of any path to that node. So what you would do here would be what? For each node, track max of each color of any path. So max, so color count is equal to 0 times 26 pixel colors, and do that for every node. For n in the length of colors. The number of colors is the length of colors matches the number of indices that would be the number of nodes. So color count is that. And then if the node isn't in a graph, just say this is a leaf, and so it's the last node. Then I think we can do something like add the current color. So color count for this node is color count for this node of the color of this node. So let's say node color is going to be color integers of this node. And color count for this node of this node color is going to be increased by 1. And then most common would be the maximum of color count for this node. And then the answer is going to be the max of answer and most common. And then you can break there or continue. So if it's a leaf, add the color leaf to however many colors you get to here. And then the most common color. Okay. And then if it's not in graph, so that means that, so here it is in graph, so that means there are children of this. So what I'd want is if the parents are still around, if reverse graph of node, the length of it is still greater than 0, then it needs to process the parent still first before processing this node. So I think what needs to happen is deck.append this node again, and then keep on going. So somewhere in the chain in the deck there's the parent waiting to be processed. Needs to process processing node, put node back in queue, put node at end of queue to be processed later. I don't know if that's the most optimal way of doing this, but it is a way, I think. So here, at this point, the parents have been processed, so now this node can be processed. So for every, and there are children of this, so for every child in the graph of this node, actually maybe I should have called these children rather than neighbors. So not really, they're more than neighbors, they're children. Whatever. For every child in the graph of this node, we're gonna first not forget to say the reverse graph this child, discard or remove. I think this can be a hard remove. Remove this parent. And then iterate through the colors and say that reaching so actually say the color, so I can here say the color count of this node color is going to increase by 1 at this point. I don't want to do this earlier because I don't want to I want to make sure that it gets here properly. And then for each color, so for color in range of 26, there's probably this optimization there that I could do. For each color in range 26, and the color count for the child of this color is equal to the max of whatever other possible paths reach that child with that color, or the current way or the current nodes. Okay, yeah, so to reach the child with some color could be whatever's currently there or through this node. And I think, okay, then you need to append deck.append the child. Maybe only append the child if the child has no parent still. So you have to do this. You have to do this parent check here. Would that work? So 0 appends 1 because there would be no parent of 1 at that point. It wouldn't append 2 because 2 still has the parent of 7. And then when 5 gets processed, 5 adds 6, 6 adds 7, 7 adds 2. Okay, maybe I can just say here, if the reverse graph of this child, the number of parents in it is equal to 0, then append the child. Maybe that can prevent this check here. Okay. This might go infinite, quite possible. Infinites are always a possibility without while loops, and my level of ability. Okay, and here I think that's otherwise it. The answer is actually 0. The object is not movable. Line 35. So 0 times 26 for n in the length of colors. Oops, n in the range of length of colors. Okay, so it kind of got nothing. Did I return 0 at some point here? No. Wait, this answer is oh boy, it's returning it inside the while loop. Key error. Each child in the graph of the node, reverse graph of the child. So let's say print the node and the child. So node 2, child 3. So reverse. Oh, it's doing it twice. Zero 1 0 2 2 3. Why would it be processing 2 twice. Okay, so let's go ahead and do print post the node, and let's say with the graph. So yeah, okay, so it did 0, then it did 2. Actually, say here, start in the node. Oh boy, oh boy, oh boy. That's a lot of starting ones. So why would it do that many 1 nodes? One is not in graph. Okay, let me go ahead and say here. And detected. So it should have detected the end of 1. And then okay, so start 0 and then start 1 that's ended. Why does it have another end detected? Okay, let's go ahead and just say post. Okay, I know what I wanted to actually put here. Post node, and then I want to know what's inside the deck. Queue. That's a lot of ones. A lot of ones for sure. So maybe start 0. For every child. Oh, holy shoot. So this if statement should be outside of the for loop. I think that's why I was returning answer in the wrong indentation. For every child, you change the color frequency of the child, and then afterwards you append the child once rather than 26 times. Okay, that seems better. So 0 adds 1 and 2. 1 is done. 2 adds 3. 3 adds 4. 4 is done. And I got too many colors. Too many colors. Oh, interesting. Let's say what the node color is here. 0 has color 0. 1 has color 1. 2 has color 0. 3 has color 2. 4 has color 0. So 0 goes to let's say I put it to end node and then most common. Okay. And detected 1, 2. That is not correct, sir. 1, 2. Because 0 goes to 1. And these are, that should be 1. Is the most common color, or most common frequency. Not the frequency of the most common. That detected 2. Color count the node in this node color. Color count of this node. Alright, fine. Let's go ahead and actually print out the color count for this node. Let's really dive into it. Oh boy, that's color count node color plus plus 1. Max color count of the child for this color. Color count of, I don't think this should be color, I think this should be node color. Yeah, this should be color actually. Okay, there we go. There we go. Let's see if that had, no, I have more points here. Okay, let's see what are the issues. Okay, so this one, I said that there was a cycle, there wasn't any. Okay. Use test case. So why did I detect that there was a cycle here? So let's say I print out my graph. The graph. Print the parents. Alright, 0 goes to 1, 2, 2 goes to 3, 7, 3 goes to a bunch of them, so on and so forth. Parents 0. So 0 is the only parent. So 0 goes to 1, which is a child, or a leaf. 2 goes to 3, 3, 7. 7 goes to 8, 8 goes to 9. 3 goes to 4, 5, 4, 5, 8, 5 goes to 6. Huh, so why did I detect those? If neighbor is in the graph, neighbor is in scene. Yeah, if neighbor in scene is not correct, is it? Yeah, because you could have multiple ways of getting to a certain spot. How do you detect cycles? Holy shit. You detect cycles using breadth first search, maybe? How do you detect cycles? So 0 goes to 1, 0 goes to 2, 1 and 2, 2 goes to 3, 7, you add 3 and 7, 3 goes to 4, 5, 8, 9, you add those suckers. This need to somehow detect cycles. So 0. So if you had something like this, and you say 2 is seen, and just because you reached a child or you've seen the child doesn't mean that you've actually gone back in a loop. Go 0, 5, 1, 2. Do you need to do... Okay, so 0, if you had something where it's a cycle, 0 goes to 1 and 1 goes to 0. 0 goes to 1 and 1 goes to 0. So 0, you add 1, and 1 you add 0. Then 1 can say that you've seen. Zero goes to 1, so it's 1 blue. 1 blue goes to 0 red. So we start from your parents. I guess if you have no parents, then this is also a cycle, right? I think probably my thing doesn't work if it's 0, 1, then 0. Probably just doesn't work. Yeah. Yeah. The parent set is empty. You can say here that if after doing the parents, then there is no parents. 0, then return 1. Okay, so at least that's a minor fix, but a fix. But in a more general case, how do I do this if there's like 0, 1, 1, 2, 2, 1, 2, 0 or something? Or I guess that's still no parents. So 0, 1, 1, 2, 2, 1. 0 would be a parent there, but it still would have a cycle. So I can go 0 to 1. 1, is it depth first? Is it depth first search for cycles? So 0 goes to 1, 1 goes to 2, 2 goes to 3. So you don't Oh, pretty sure I must have done a problem with cycles before. Or if not done a problem, had it taught about at some point. Alright, this is kind of cheating, but cycles in a graph. How do you detect what is the optimal? What is the optimal way of doing this? Maintain the visited. Do a depth first search. If the graph is disconnected, then get the depth first search force and check to see if cycles checking back. Using topical sorting, using depth first search. If the graph is disconnected, then depth search. Get the depth search force and check the cycle in individual graphs by checking back edges. So adjacent, no, what's adjacent you? Okay, so maintain visited and recursion stack to track nodes in the current. Okay, so you have a stack and you have a visited set or array, whatever. Start depth search from any unvisited node. Mark it as visit and add to the recursion stack. Add it to the recursion stack and recurse for all adjacent nodes. Okay. Sure. If node 1 is adjacent to node 0, traverse node 1, call depth search and mark it as visited. Node 2 is adjacent to node 1, traverse node 2 and call depth search. Node 3 is adjacent to node 2. Node 3 has no adjacent, so backtrack. Backtrack and mark it from the recursion stack as is no longer part of the current thing. While traversing nodes 2 adjacent to node 0 is already marked in the recursion stack, confirm it as the present of the cycle. While traversing nodes 2 adjacent to node 0. Huh. This is not something that I recall coming across. Okay. Easiest way is to detect is to use a memo field to the node struct, walk the graph, set each node you visit as to a consistent value. It's guaranteed not to be already on a node. Use a global counter. If you visit a node that already has that number, you have a cyclic graph. Interesting. So you traverse the graph. Label V is discovered for all directed edges from V to W that are in the G adjacent edges to if the vertex is not labeled as discovered, then recursively call ds. G dot adjacent edges of V depends on your graph implementation. Label V is discovered and vertex W is not labeled as discovered depends on. The graph is not guaranteed to be rooted and connected. That is, in general, there is not a vertex from which all vertices are reachable. You need to call the above algorithms repeatedly using vertices. Yeah, I think yeah, so there's a reference to the rabbit and hare problem, or rabbit and turtle problem, where you can detect cycles in a linked list using like a fast pointer and a slow pointer, where one fast pointer goes down twice and the slow pointer goes down once for each connection, and at some point the cycle is detected when the fast pointer comes across the slow pointer. But that was a cycle within a linked list. I don't recall actually studying cycles in graphs. Not recently, anyways. Okay. Detect cycle in undirected graph. Or maybe I did detect cycle in undirected graph, actually. But this is a directed graph. Let's see. Let's do one more Reddit post here. Depth first search and keep track of the nodes that you've already visited in a stack, popping off and moving backwards. If you're in a node that exists in the stack, you've detected. If you are at a node that exists in the stack, you've detected a cycle. Interesting. Depth first search, keep track of the nodes that you've already visited in the stack, popping off and moving backwards. So you need to move forwards and backwards when detecting cycles. Technically speaking, in an indirect graph, there is a cycle as long as an edge exists, node connected to another node, node connected to another node, or node itself. Distinction can be important if you do pathfinding, example with 0 or negative weights. In a direct graph, a cycle is present if starting at node A, recursively revisiting any child by depth first search. You ended visiting node A once again. Instead, it's once you visit a node already visited during the graph. If we take an example, 1 is a parent of 2 and 3, 2 is a parent of 3, we can see that this graph contains no cycle. 1 is the parent of 2 and 3, 2 is the parent of 3. Okay, I agree. We can prove that no cycle connects to cycle using Wiki's algorithm to start node 1. Node 1 we haven't visited anything. Visit node 2. Now we've visited node 1 and 2, and then we visit node 3. Since 3 is a term node, we can indicate that it can't be part of a cycle. Since node 2 leads to no other nodes, there were no cycles, we indicate it cannot be part of a cycle. We visit node 3. Since we indicated node 3 is not part of a cycle, we skip it. Since 1 leads to no other nodes, so finding cycles using depth first search by traversing a graph using get something depth first search trees is maintaining a reordering of the graph vertices, and after building the depth first search trees, have the edges classified as tree edges, forward edges, back edges, cross edges. We notice that edge EB is marked as a back edge in the previous example. Back edge is an edge that is connecting one of the vertices to one of its parents. We also have AC marked as forward edge connecting a parent to one of its non-direct children. Notice that we also have normal edges. Where's the code? Where's the code? Start. Oh Lord. What is this? Forget what this is called. Like Universal Marking Language, UML. Diagrams. Unified Modeling Language. Universal Marking Language. I don't know what branch of engineering or system design or what have you uses these things, but I definitely never took any course in it, but I always found it to be quite confusing actually. Well, I guess it's just like if statements are certain shapes, and I don't know, branching stuff is other shapes or something. Yeah. Anyways, you have visited set, you have indices 0. Oh my lord. This is just so unnecessary. So you have an array of visited. And then what? So the first function is iterative. Maybe I'm just approaching this wrong. I just want a quick answer, and this is not a quick answer. For each vertex in the graph vertices, if it hasn't been visited, create an empty stack. Push it onto the stack. Say that you visited it. Detected cycles is an empty list, and then call process the tree is a recursive function that takes the graph, the visited list, and a stack. After that, the function is mainly doing depth first search, but also marks the found vertices as in stack when they are found. After processing the vertex, Mark it as done in case we find a vertex that's in stack, we found a back edge, which indicates cycles. Okay. I think so. Part of the issue is like it's something that I feel like I might have or should have known. So I want to like quickly get back to that point of knowing it, but none of these things actually fully is recognized in my data banks currently. So I don't quite know if I just need to learn it right now or if I just need to recall how I learned it before. This Python code. So there's two functions. Constructed adjacents, okay, is cyclic. So you have a list of vertices, edges. So constructed builds the adjacency list from the edge list. Okay. The adjacency list is pretty much the thing that I always use for graphs. The list of edges list of nodes that are adjacent to any given node. Yeah. So you have a visited set and a recursive stack. Try depth first search from each vertex. So we start with each node, assuming it's not visited, then if it's not visited and this utility function is true, then return true, then you detect a cycle. So the utility function does what? So the utility function takes the graph, the node, things that you visited, and the recursion stack. If the node is already in the current recursion stack, a cycle is detected. Okay. When do you set the current recursion stack to true? Mark the current node as visited and add to the recursion stack. Recur to all adjacent vertices. This is not what I want. What? I don't want a recursive version of this. Maybe a recursive version of this is necessary. Non-recursive detection cycle, Python, direct graph. Cycles and a directed graph using iterative depth first search. Okay. Visited is set or array, sure. You have a stack. You have a start node in the graph. If you haven't visited it, then push the start node to state 1 while the stack exists. Pop off the stack. If the state is 1, then you're entering the node. Huh. push start node with state 1 entering. If state is 1, then visited node return true. If we're entering a node that we visited, then a cycle is detected. And then we set visited to be this node to be true. And then otherwise we pushed push node with state. So if we're entering the node, then we push onto the stack, exiting the node. Add neighbors to the stack in reverse order of insertion. Reverse order of insertion. Graph.get node reversed. Add neighbors to the stack in reversed order of insertion. So interesting. Every neighbor in neighbors. Okay, this is definitely something that was different than the previous stuff that I've seen. Okay, so what's gonna happen here? So you start with a node. You say if you haven't visited before, then you're going to say that you're now entering it. Visited start node is 0. So this is only going to be true once. Yes. The visited start node is 0. So if you have visited in any fashion, then so this is basically your parents, right? Your parents can't be something that you visited in any fashion before, because your parents don't have children that can connect to it. So for every parent in graph, basically. So you say that that's going to be your start node. And then while your stack exists, take the node that's currently off the top. So this is stack, not a queue. Okay, take the node off the top. And when you pop it onto the stack, you push it in state 1 to enter the node. So we're entering the start node. And then when you pop it off, if the state was something where we entered that node and we have visited that node already, then it's a cycle. So once we've entered a node, we say that we've visited the node. And now add onto the stack, exit the node. Interesting. So currently the stack, so let's say you have node A. So you can say that you enter node A and then you push onto the stack immediately that you want to exit node A. But since it's a stack, we're also going to push the children of node A onto the stack as well. So the child gets processed. Children gets processed in reverse order because somehow that matters. And then, so for each child gets processed. When did I set my visited to be 1? Set to 1 here. Okay. So every neighbor neighbors, if visited the neighbors is not equal to 2. The visited So visit is in a set, it's a state. So unvisited, visiting, and visited. Huh. So you haven't seen it before. You have seen it before. Visiting. Interesting. So it's only a cycle if you're currently visiting, like you're currently on the path. But if it's a separate path fall. So if visited, every neighbors, if visited the neighbor, so if you haven't visited the neighbor, then you add the neighbor into it. And you're currently visiting. Yeah, so if you're currently visiting, ooh, two things is one, can I understand it, and two, can I replicate it without having to actually resort to this? So you have your start node. Okay. Okay. So detect cycle if exists, return -1 if there is. Okay, so this is the incorrect way of detecting cycles. So for every node and parents, I'm pretty sure this is fine. Visiting state. Visit state is 0 for the number of nodes, which is the length of, say, n is the length of colors, which is the number of nodes. And here is 0 is unvisited, 1 is visiting, 0 unvisited, 1 visiting, and 2 visited. Okay. So for every node and parents, if the visiting state of this node is not equal to unvisited, then continuing, I think, is fine there. So this thing is only true if it's 0, which is unvisited. But if it's not 0, then continue. Okay. But actually, I'm already dealing with parents, so do I need this? Yeah. So if I'm already dealing with parents, then maybe I just need a visiting and visited state, or a visit and unvisited state. Okay, I don't know. And I need a stack that's created outside the Actually, I can probably maybe make this node in graph to make it, and then test my theory that it's capable of doing parents only. And then I add that node to the stack, I want to say. Oh, yeah. Stack.append this node and one state. And while the stack is this, the node and state is going to be popped from the stack. And if the state is 1, else if the state is 2, is the 2 branches here. Yeah, I mean, it's not really going to test state 0, right? Okay. So entering node is what we're doing here. So if the state is 1, then this is entering. If the state is 1 and we're visiting it, if the visit state of this node is 1 already, then this is a second way of visiting it. Yeah. So if the visit state is not entering, then we set the visited for this node to be 1. Didn't we already set this node visit state to 1 already? Okay. And then what? Staff.append node 2. Push onto it the exit state. Okay. If we're entering it, then append itself, and then here we have to append the neighbors or the children to it. So for every neighbor in the graph of the node, in reverse order, right? In reverse order. And then, oh, I'm using nodes, oops. Every, I think this should be parent. Actually, let's say it's every p node in the graph. Parent node appends. Okay, and then the node is popped. For every neighbor in the graph of the node, every neighbor in the graph of the node. And I think here it might be that there are no neighbors. If node not in graph, then continue. Yeah, skip it. So otherwise there are children for every neighbor in graph. The node in reverse order. Stack. Do I need to check the state of this neighbor? If the visit state of the neighbor is not equal to 2, so we haven't visited the neighbor. So the neighbor's unvisited or visiting, but not visited. If the graph of the visit state of the neighbor not equal to -2, then stack.append the neighbor with the state of 1, let's say. Okay. Else if state is 2, then visited or visit state of this node is going to be equal to 2. Okay. I think this is a copy of that code. And it's still getting this wrong. Shucks. Oh wait, I don't think I removed my old way of detecting cycles. Okay. Well, it's running slowly, incorrectly. Oh, what's going on here? There's no edges. Okay, that's stupid. Okay, if length of edges is equal to 0, that's kind of silly. Oh, alright, if length of edges is equal to 0, then the answer is just 1, not -1. Because it's not a cycle, but use that one color. Okay. So, interesting. Timed out on the thing. Let's go ahead and print out the graph here. Yeah, the graph takes this long. Oh, I probably need to print out the graph and return. Okay. So the graph is this. 0 goes to that. And let's go print out the graph and the parents. Actually, I think I'd like to try this thing with the in parents. Um, let me not use this return statement. So time limit exceeded would probably still be for that test case. Yeah. Okay, so yeah, this thing does work with this my detection of the parent nodes. I don't know if I need the 0 explicit state, but I think that's fine too though. So let's go ahead and return 0 here. Print out the graph. Okay. So parents, sure, this seems fine. So it should be 15. It's taking too long to figure out what the 15. So if you have the deck, take the node, take the color of the node. If the node is not in graph, the node is not in graph. So it's a leaf. Then add 1 and say you're done. Is this happening multiple times? I think so. Okay, I don't think this is giving me much in terms of useful output. So let me just go ahead and say print what the node is, start and the node color is, and see what the actual what it's actually trying to do. Say count is 0, count plus equals 1, print this out, and if the count is 1000, then return negative. Okay, am I still returning 0 at some point? Okay, so should be able to print out 1000 things. Should go time limit exceeded. Is it going infinite somehow? Okay. There's no while loops in here really. Okay, let's go with 100 rather than 1000. I wonder if it's going infinite here. This is the place where there's only a while loop. Yeah, I think maybe it's going infinite here. Let's say count is 0 here. Okay, so it's in the cycle detection. Interesting. Okay, let's go back to the. This one still is not gonna have an issue, I think. Or it still has the same issue. Yeah. So why is it detecting? So this thing should. This thing should give me a wrong answer. The answer should be 15. Interesting. So return false otherwise. So if it goes through here, then returns true if it's a cycle. Huh, interesting. So if you have a visited node, you append the node in state 1 while there's nodes in the stack. The node in state of the stack. If the node is 1, then you're entering it. So you say that visited node is equal to 1. Or if it's already entering, then it's going to be returning that there's a cycle. Otherwise, you say that you're visiting the node 1 and you append the exit tuple on the stack. The node is not graphed. Maybe this is an issue. This is the difference between what the AI gave me. Yes. Yeah. The reason I add this thing is because changing stuff. I don't think this is an issue. Node is not in graph and continue. Yeah, because it continue if there are actual children of that node. For every neighbor in the graph node in reverse order. Add neighbors to stack in reverse order of insertion. I'm not sure what reverse order of insertion might actually be. I think it was reverse order of the. Okay, let me try it for every neighbor in the graph. Just add it to the state. Still too long. Visit state equals visit state neighbor neighbor 2. Okay, that's the visited. Now let's take the visit state. State is 2, then visit state of this node is going to 2. Okay, so that's what I kind of want to know is what is the actual state of stack. And maybe just do 100 iterations. Zero, 2. Zero, 2, 1, 1. 2, 3, 4, 1. So I must be adding stuff without popping. 0, 2. Okay, let's go 200. I feel like it's probably something here. Because it really shouldn't be adding 200 times. Or 1,000 times. Adding 95, 92, 94. Oh. Okay, I think maybe print start staff node state. Maybe now let me just not see the stack. Ninety-five 1, 95 2, 95 1, 95 2. Either this algorithm is actually not correct, or I miscoded the way to do this. Entering state. Oh, how much do I trust this algorithm that Google gave me? Guess I probably should understand it better if I don't have issues with it. Entering node state 1. Push node state 2 on the stack. Why is this? It doesn't matter if this is reversed order. For every neighbors, if this state of neighbors not equal to 2. Visit state of the neighbors not equal to 2. Append, add, append neighbor visit state 1. Else if the state is 2. So the stack is what we're going to do at a node without visiting it. And when we process the stack, when we visit a node, say that we're visiting it. So we're down a path where it's not active. But if we're down a path where it's active and we're visiting it again, then the cycle is detected. And when we visit a node, we push onto a stack that the exit state, so that we eventually process that we're exiting the stack, exiting the node after we've done processing all its neighbors. I don't know why you need to do the reverse order of insertion here. Add neighbors to stack in reverse order of insertion. Graph. Get the node. For every neighbor and neighbors, visited neighbors. So then, say I have 1 goes to 2, 2 goes to 3. But when I check to see if the visit state of 2 is there, the visited neighbor 2. Stack append neighbor 1. So we haven't visited it. Because if we have visited it and we detected it, if we have visited and we detected that there was no cycle, then we don't need to go down that path again. Okay. So visit state. So for neighbor that we haven't detected that it's a cycle, then we add it to the stack. Huh. Okay. So why did this one go 1, 2, 1, 2, 1, 2 a bunch of times for 95? We entered state 92, exit state 92. and then enter state 92 and exit state 92. If state is 1, if the visit state is 0, visit state is 0. Did I actually do that correctly? Okay, maybe I every start node. I wonder if the visit state did I? Every start node. Okay, so this is actually do exactly what it has. So every parent, let's say start node in graph, if the visit state of the start node is 0, then do all this jazz, right? Stack.append. I feel like it should still be the same thing. Yes, we'll do it 2,200 times. And I think this thing probably goes to 20,000, probably too much. 2,000 is probably too much as well. Yeah. Get stuck on 91, 92. So while stack. So why is it entering again something that is already visited? Why is it entering again something that's already visited? If state is 1, we're entering it. So it should say the visited of that state is 2. Visit of that state is 2. Boom, 90. It's going back to back. It's entering 95 and it's exiting 95. So when it enters 95, I assume 95 is like a dead end. I assume 95 has no connection. Every node in graph and node and graph node. So 94 goes to 95, but 95 goes to nothing. That's fine. And then, so 95 goes to 1, so you enter 95. Enter 95, but 95 has nothing. So enter 95. You should still pen 2. And then if it says 2, then you should be setting the visit state of that 95 to 2. And ending 95 like a lot of times. So why would it possibly take between that? Because it should get the visit state of the neighbors -2. Somehow resetting the stack state, the visit state. Visit state of the node. Starting stack 94, ending 94, starting stack 87, start stack 84 again, 86, 94, 95. Every neighbor in the graphic node, the visit state of the neighbor is not equal to -2. Stack.pen neighbor 1. And then let me go ahead and print size of stack to the length of stack. Is the length strictly increasing all the time, pretty much? Length, no, it's just going up and down, up and down. Well, upwards, downwards, slightly increasing, but generally not always increasing. I guess there's only so the state is 1. If the state is 1, if the visit state of the node is 1, return -1. Otherwise, set the visit state of the node to 1. E5 has no neighbors. So when you reach 95, so for every neighbor, it should only ever get to state negative state. Oh my god. Oh my god. That is so stupid. I'm just so stupid. All that for a single, well, it's not a single, it's a negative sign. That shouldn't have been there. I wish I could read. I wish I could read. let's go remove that, remove the count. See if this removes my printouts for the most part. Count is not associated with anything. Node color counters. Node color. What is wrong with this line? Oh, count this was. Okay, there's still some printouts. Oh, that was stupid. Well, at least that second pass really forced me to understand what the hell was going on. It looked like it was going right, which it was. It was just my mistake. I'm gonna fix this and say if, go back to my other one, is if it's not equal to 0, then continue. Although I'm also gonna go back to this thing and start back in the parents. Because that should also have been fine. Alright, so this is probably never going to be optimal because I really am done with this one. But I will try to spend a few minutes to optimize what the hell I wrote. Okay, so let's go ahead and run it one more time. So I think maybe you can check the length of the edges being 0 immediately. And parents is a set of all values. I think maybe you don't need parents, right? Parents. I guess you start with parents here. No, this is fine. So you start with parent set. Can you make this faster if you didn't have a set? You just had these are node values, right? So node values are just numbers between 0 and 9. So maybe if you just said, you don't need, yeah, you don't actually need this. You just say, every time you see an edge, parents can be just be true for every node. And if, no, I guess, is it false? Well, set range of n. So you have all the parents there. And you have all the parents there. And you remove parents when you do this. Parents dot discard b. It's fine. Okay. And if the length of parents is 0, then that's fine too. First graph is a set. I guess you could do reverse set is a set of parent nodes. I think this is probably fine. Graph is a default dictionary of lists. That's fine too. Is this a stack? K count is not used anymore. For every start node in parents, this state of the start node is to zeros. It's fine. Stack goes into that stuff. This is all fine. Visit state is to convert to color values. Okay, so what I could do here that's better is I'm going through all 26 colors, but if there are some colors that are used and some colors that aren't, then maybe I can just go through those colors that are actually in use. So maybe I can say what can I say here? The color integers are going to be, so let's say there's 3 characters. So it could be something like use colors is creating a list or set. I don't think it matters. The list. So I can probably use comprehension here. Use colors is going to be from my colors, the set of colors. The set. So color integer is the ordinal of, so what is color integer? It's like 0, 1, 2. Color integer. Oh, it's color int actually. So color integer is the list of colors in use. Okay, so I want a set of that, right? I want just a set. So use colors is equal to a set in that list of color integers. And then color count. This is a little too big, but maybe it's fine. Because only certain of these 26 are in use. But for every child and every color in the range, every color in the use colors, and then I can do that. Find the maximum. Okay, I think that's slightly better. Still, still return 0. Okay, slightly faster. Doesn't go through 26 colors each time, and then it goes through the limit set. 2, 1, 2, 1, 2, 1, 1, 2. Huh. This was previously detected as wrong. But now it's not. The length of parents is 0. Okay, I guess my new detection of parents is incorrect. Boy, what is my parents here actually? Yeah, parents, so here there's 2 nodes. So my previous way of detecting parents was adding to a list of nodes and then removing it. adding to list nodes and then removing nodes. Right. So here currently I have like maybe 0 as a parent. Zero as a parent. Whereas previously I had nothing as a parent because 0 was never added to the list of parents. Okay, so that's right. So not all nodes might be in the edges, in the list of edges. So I could do something like if so I have no parents. Well, so 0 is considered parent here. 0 is considered parent here. Alright, just going back to the other way of doing this. So parents is going to be A, B, and edges, parents dot add A and B. Okay. This should go back to the thing. Okay. Holy Jesus. Okay. I can do better in memory. Yeah, I can do a lot better in memory. The size of the color thing here is not great. This times 26. But only certain colors are actually used. So I could possibly use a dictionary. I could map use colors to certain indices. So the color count would be the length of used colors, and then you map so something like this for every n. So the length of colors is an n. And the length of the number of used colors. And color index is equal to, so for every, so let's say used colors is the set. Why do we even need a set here? I'm just using used colors as the list. Or whatever. So for every index in the range of color int, in the range of the length of color integers, color index of this color values the color int of this index. color index of, so color, I wonder if I should sort this. Maybe I should sort this, or I can just convert it to 0 through I can convert it to 0 through n. Where do I make use of? So for every letter, change the letter to a number, and then remap the number. Eeks. So I have a, I didn't print out, so let's say if I have an array of color integers, like some random set like this. Oh, Jesus. So if I have a color array of color integers like this, 0, 1, 0, 2, 0, but more exotic like this, 7, 7. So I'm thinking about mapping these to like 0 through a number of different types, so that I can use that number in the second array directly rather than dictionary or something like that. I prefer using indices rather than having to hash indices in an array. So for every color I need to, so the color integers, I need to make a set so that I know what are the used colors, and I need to convert that to a list. So let's say used colors is the set of color integers, and then I'm going to do a mapping. So set and then list. And then I'll say mapping is a dictionary. I don't know if this is the best way of doing this, but where for every C in used colors, actually for every index in used colors, mapping for the color itself is mapping for the used color itself is equal to the index. So let's say the color is equal to used colors equals index. Mapping for this color is equal to index. And then I can do modified colors is equal to an empty array for every color int, and let's say I and color int, then mod colors dot append mapping I. And let's go ahead and print the mod colors. Colors use color. Use color is a index in the length of use colors. This is not how you create a list from a set. So in the range of the length of the number of use colors. Just definitely slowing down mentally. Okay, so okay, that's good. So the 7, 7, 17, whatever became that. So now I can just use the mod colors. So I don't know if I need this anymore. So where do I use color int? The node colors can be the mod colors. And I think I roughly made that the only way I use colors so far. Not quite. Next out of range. So it's multiplied by the length of the number of used colors. So which color is out of range here? Length of the number of used color. Okay, let's go ahead and print out range of node, node color, and the length of the number of used colors. So at some point it's going to crash. Okay. Let's go ahead and print out the mod colors here. So 0, okay. Every child, every color, and every color in the number of used colors. Okay, this is the same issue. This should be the range of the length of used colors. Well, yeah, range, I'll say n colors is the length of used colors. And this is going to be in the range of n colors. And it's going to just be in colors. Standard out, remove prints. Okay, so it was like 115 megabytes before. This should be much less, much more compact. Yeah. Okay. So 96 megabytes is like halfway there. It's not too far. Okay. Alright, so what's happening here? What is happening here? I think I'm gonna finally do my end summary. So first step is creating the graph and the reverse graph, which helps to do other things later on. The reverse graph is just for every node, what are the parents of it? For each node, the set of parent nodes. And here I'm referring to children and parents as parent as the node A that leads to node B, and B is the child node of A. So for every edge, if it's the same node going to itself, then obviously that's a cycle, and that's returning -1. Otherwise, you add that add the child to the adjacency list or the graph of the parent node, and you also do the parent node is added to the set of parents for the child node. And I keep track of a list of nodes that are parents, and this list of nodes is nodes that have children and no parents. So basically I start off every node that has an edge is possibly a parent. Nodes that have children and no parents. Actually, I should probably start with parents.add A, not add B. I don't know why I would add B. Yeah. So I would add A to get the list of all nodes that can be parents. And then if I see a child, then I remove that child from the nodes of parents. And this is useful later on. If there are no parent nodes, then basically there's a cycle there. Although I detect cycles later on in another fashion, so I don't think actually this is necessary. I think I detect cycles using some other method later on that's more. Oh gosh, I guess I don't. Okay, never mind. Never mind. The name parents. Huh, that's interesting. In any case, so let me double check if that still works. So then, this whole code is this is generic detection of cycles in a directed graph, and there's a lot of ways that this can be done if you Google it, but this is a pretty concise way that the AI generated on the Google search. So there's a visit state for each node that's initially 0 for being unvisited. Anytime you visit a state, then you set it to visiting, and you use a stack to immediately push onto a so you have a stack that processes the various states, the nodes that you've been to, and what state that you're kind of that you're visiting with. So you can either visit or kind of exit a node. So when you enter a node or when you visit it, you immediately append to a stack, push onto a stack the exit exit action. And so if it's a node that's like has no child, so it's a leaf, then you immediately enter and exit it. And when you exit it, you set the state, kind of this meta state data structure to be or to be exited for that node. So later on, when you're checking for nodes, you only check for nodes that have not been exited. Because if you let's say you go 3 to 4 and you check that 4 is all good, then that means that if there was another way to get to 4, like 5 to 4, then because 4 has already been visited and we know that 4 doesn't lead to any cycles, then you don't actually need to add 4 to the list. But if you're entering 4 and you see 3 again, or a state that you're still visiting, then it means that you haven't exited that kind of loop, and therefore it's a cycle. Anyways, it is kind of boilerplate in terms of how you want to code that. And then, so here, this is post, this is graph has no cycles, and this is the actual, this is the main problem. So how do you count the number of most common things? One is to make it a little more data friendly, compact. I convert the colors to an integer array of values. So so for instance, if you had something like this, then z would be converted to 26 A's 0. So it'd be like 26 0 0 26 0. There's 26 letters, so it's 25 0 0 25 0 25 whatever. So that's the color integer version of it, and then because not all colors are used, then I do this other process to make into a version of that where it's only using 0 through the number of colors that were used. I don't think that's strictly, it's just for memory purposes. But besides that, like the main thing that you do here is for every node in the graph, you track the number of colors for every node in the graph, so that's n. You track the number of colors, the maximum number of colors that can be, the maximum for each color. Okay, for each color, you track the number of nodes that lead up to this node using that color maximally. So for instance, if you go to a certain node and there's like a path that leads to it that has like 5 reds, another path that leads to it that has 4 reds, then you track both. You say that up to this node, for this color, there could be a path that's 5 and a path that's 4. So for every color, and for every node that you need to track that. And so you start with your parent nodes. So these nodes can always lead to other nodes, but they cannot. Hopefully you don't backtrack, right? And if you start with parents, then any path that you take is not going to have a higher path color, higher color count for any other path. So so for every parent node, starting with the parent nodes, you take any node itself. If the node has no children, this is a leaf, and then we can calculate answer, update answer with the counts here. So again, for every child that you have, then you look at the paths, the colors for the paths. So you take the color of the node itself, you add 1 to the count of that color for for this node, and then you take the most common color for this node, and if it's more than the answer, then the answer increases. Otherwise, if it's not a leaf node, then again, you increment the color count for this node by 1 using the color of the node, using the color of that, yeah. And then for every child, here is the tricky part. You don't want to process a child. Normally, like when you search for graphs, you'd add every child to like the queue of the graph. But here, you only add the child if all the parents are done. So only kind of interpret. Actually, so I think it's wrong order of explanation. So for every child, and maybe I'm doing this. Okay, so something like this. So you remove the parent from consideration for this child node. And this is necessary so that you track how many parents have reached this node, this child node. And you only process any child node if all the parents have reached it, because you want to close out the possibility that there was like maybe 2 ways of reaching 4, like 0 to 4 and another way of reaching 4. And currently seen as like there's 3 reds that can be led to 4, but there could be another way that led to 4 that was like 5 reds. So if only process 4 once you have reached 4 through all the other parents, or you kind of eliminate all the parents from having been processed. So that's this thing right here. That's really the key part, I think, having some way to track that. And then for that child node, basically compare the current count of ways of reaching this current node with every color versus the ways of reaching that child node with that color. So like if I'm at 3 and there's currently 2 ways of reaching 3 with red, then I can say that there's 2 ways of reaching 4 with red, assuming that 2 is the biggest way of reaching red with 4 that I know of. So and then again, if there's like 1 way of reaching this node with blue, then I can say that I can reach 4 with blue with 1 blue as well. That's for every color, and that's the main update. So in summary, create some data structure to traverse graph. And here I used the default dictionary. I could have possibly also used a matrix, a 2D matrix maybe. Nah, I think the default dictionary list is probably fine. Have logic to remove cycles, and again there was a few checks for cycles. This was like no A equals B, and then this was also use DFS and kind of visit state array to determine if visit state array and stack to determine if this occurred, if visiting an active path. In which case this means this is the cycle. Then this was not strictly necessary, optional. Is convert color string or letters to integers. This is index like A 0, Z equals 25, so on. And more optionally is map colors used to minimal set. So for instance, like let's say your colors were at 7, 4, 1, and 10 to 0, 1, 2, 3, 4, 0, 1, 2, 3. Again, that's just for memory purposes. But the other thing is for main problem, have data structure, in which case I had a 2D matrix to store to store for each color and node the highest path the most any path can have to reach that node with that color. So this is this color count deal for each color used and for each node we play. And then starting with parent nodes that have no parents. Process each node using a deck, doubling a queue. Using a queue whereby the node will update all its children's color counts to be the max of itself and the child's count for each color. So if 3 leads to 4 and 3 has 2 blues reaching 3, then I can say 4 can reach with 2 blues if that's higher than what it currently has. So if 4 already has another path that reaches that with like 5 blues, then it doesn't update. So that is this thing with me. And then also only process child, basically add to queue if all parents have been processed. So all paths to child have been accounted for. And here I used a set to track set of parents for each node to track that. So when I create my graph for each child node, I create a set of parents, and then for each time I traverse or which I kind of look at a child node to update its counts, I remove that parent from the child set. Time complexity, this is going to be O of the number of nodes. So let's say n is the number of colors, the length of the color string, which is the number of nodes, right? So that's the number of nodes and this is going to be O of n. You go through each node at least once, and O of, you go through each edge at least once to determine when that cycles. And you need to go through every node at least once to determine most common. So I think this is going to be O of n plus e. Where, what is e? E is the vertices? No, edge. Yeah, so I don't think you, oh, you also need to go through a color. So yeah, so C equals number of colors, n is number of nodes, e is number of edges, O of e to determine cycles, O of n to determine most, so O of n times C. I guess for every node you need to update the maximum color of subsequent ones. So I think it's made O of n times C times, no, it's not times E, plus E, something like that. So update every color count for each node. Yeah, space complexity, this is going to be O of n times C for matrix of colors and color counts. And the visit state is O of n, O of n for visit states to check for cycles. Alright, I'm done.